Hashtag space is hiding evidence of something older than the universe. The universe began 13.8 billion years ago. That is what we have been told. That is what the equations say. That is what the light confirms. The cosmic microwave background radiation, a faint whisper of energy spread across every direction we can observe, marks the moment when space became transparent, when photons finally escaped the primordial fog and began their journey through emptiness. We have measured this light. We have analyzed its temperature. We have mapped its fluctuations. The universe, according to our best models, emerged from a singularity, expanded through a period of violent inflation, cooled into matter, and eventually formed the galaxies, stars, and planets we see today. This is the story we teach. This is the framework we trust. But there are cracks in the foundation, and some of those cracks are not small. In the beginning, there was nothing. Then there was everything. That compression of events into a single sentence hides an ocean of uncertainty. We know the universe was once extraordinarily hot and dense. We know it expanded. We know it cooled. But we do not know what came before the expansion. We do not know what triggered it. We do not even know if the question itself makes sense, because time as we understand it may not have existed before the Big Bang. Time could be a property of this universe, not a stage upon which the universe acts. And yet, when we look deep into space, when we push our instruments to their limits and peer back toward the beginning, we see things that should not be there. Galaxies form slowly. They require time. Hydrogen and helium, the primordial elements, must collapse under gravity. Stars must ignite. Those stars must fuse heavier elements in their cores. They must explode. The debris must scatter. New stars must form from that enriched material. Galaxies must collide, merge, and grow. This process takes billions of years. The first galaxies, according to our models, should have been small, irregular, chaotic. They should have appeared no earlier than a few 100 million years after the Big Bang. But the James Webb Space Telescope has found galaxies that are too large, too structured, too mature, existing at times when they should not yet exist. These are not small discrepancies. These are galaxies with the mass and complexity of the Milky Way, shining in an era when the universe was still an infant. One explanation is that our models are wrong. Perhaps star formation was more efficient in the early universe than we assumed. Perhaps dark matter, the invisible scaffolding that holds galaxies together, clumped more quickly than predicted. Perhaps the first stars were more massive, burned hotter, and seeded their surroundings with heavy elements faster than we thought possible. These are reasonable adjustments. Science is built on revision. But there is another possibility, one that is less comfortable. What if these galaxies are not anomalies? What if they are evidence of something we have been unwilling to consider? The cosmic microwave background is not perfectly smooth. It contains tiny variations in temperature, fluctuations on the order of 1 part in 100,000. These fluctuations are the seeds of all structure in the universe. Where the radiation is slightly hotter, matter was slightly denser. Where it is slightly cooler, matter was slightly more dispersed. Gravity amplified these differences over billions of years, turning small ripples into vast cosmic filaments, clusters, and voids. We have mapped these fluctuations with extraordinary precision. We have compared them to predictions. The match is nearly perfect. Nearly, but not entirely. There are anomalies in the cosmic microwave background that no one talks about outside specialized conferences. There are cold spots, regions where the temperature is lower than it should be, without a clear explanation. There are alignments, patterns in the fluctuations that seem to point in specific directions, as if the universe has a preferred orientation. This should not happen. The universe, at its largest scales, should be isotropic, meaning it should look the same in every direction. But it does not. There is a feature called the axis of evil, an alignment of the largest temperature variations that seems to trace a line through space. The name is half joking, but the phenomenon is real. Some scientists dismiss it as a statistical fluke. Others suggest it could be evidence of something that existed before inflation, something that left a mark on the universe we inherited. Inflation is the theory that the universe underwent a brief period of exponential expansion in the first fractions of a second after the Big Bang. In less than a billionth of a trillionth of a trillionth of a second, the universe grew from smaller than an atom to larger than a galaxy. This solves many problems. It explains why the universe is so flat, why it is so uniform, why distant regions that should never have been in contact have the same temperature. But inflation also raises questions. What started it? What stopped it? And what existed before it began? If inflation is correct, then the universe we observe is only a tiny patch of a much larger structure. Inflation should still be happening elsewhere, beyond our horizon, creating an infinite number of bubble universes, each with its own properties, its own laws of physics. We are trapped inside one bubble, unable to see beyond the edge of our own observable universe. But if inflation can start, perhaps it can also inherit. Perhaps the conditions that triggered inflation were not random. Perhaps they were shaped by something older. There is a concept in physics called eternal inflation. Once inflation begins, it may never fully stop. It continues in most regions of space, but occasionally in small pockets, it ends and a universe like ours forms. These pockets are separated by vast distances, expanding space between them growing faster than light can travel. They cannot communicate. They cannot interact. But they share a common origin, a common inflating background. And that background, that inflating space, must have come from somewhere. Some models suggest that inflation is cyclical. Universes are born, expand, age, and eventually collapse or fade, but the process that creates them continues. Others propose that inflation emerged from a quantum fluctuation, a random blip in a pre-existing vacuum. But a vacuum is not nothing. A vacuum has properties. It has energy. It has dimensions. A vacuum is something, and if a vacuum existed before a universe, then something existed before the Big Bang. We have found structures in the universe that are older than they should be. Not just galaxies, not just stars, quasars, the brilliant cores of supermassive black holes, shine in the early universe with a ferocity that requires millions or billions of solar masses. Black holes grow by consuming matter. They start small and accumulate mass over time. But some quasars existed less than 1 billion years after the Big Bang, and their black holes are enormous, far too large to have grown in the time available. Either they formed through a process we do not understand, or they had more time than we think. There are also cosmic voids, regions of space where galaxies are sparse, where matter seems to have been pushed away. These voids are enormous, hundreds of millions of light years across. They are not empty. They contain faint galaxies, wisps of gas, dark matter. But they are underdense, and they are arranged in patterns. The voids form a network, a cosmic web, with filaments of galaxies stretched between them like strands in a net. This structure is predicted by our models, but the scale surprises us. Some voids are so large that there should not have been enough time for them to form. Gravity pulls matter together, but it also pulls matter away from empty regions, and both processes take time. One of the largest known structures is the Hercules Corona Borealis Great Wall, a cluster of galaxy clusters spanning 10 billion light years. It is so large that light takes 10 billion years to cross it. This structure should not exist. According to the cosmological principle, the universe should be homogeneous at large scales. There should be no structures larger than a certain size, because there has not been enough time since the Big Bang for gravity to organize matter on such scales. And yet, there it is shining in the data, undeniable. We have also detected anomalies in the motion of galaxies. Galaxies are not stationary. They move through space, pulled by gravity, pushed by the expansion of the universe. When we measure their velocities, we expect them to follow predictable patterns. Most do, but there are regions where galaxies are moving in unexpected directions, as if pulled by something we cannot see. This phenomenon is called peculiar velocity, and it is not unusual in small amounts. Every galaxy has some peculiar motion. But when large numbers of galaxies in a vast region are all moving in the same direction, faster than expansion alone would suggest. It indicates the presence of an enormous mass, something massive enough to exert a pull across hundreds of millions of light years. The Great Attractor is one such mass. It lies in the direction of the constellation Centaurus, hidden behind the plane of our galaxy, obscured by dust and stars. We cannot see it directly, but we can measure its effect. Our Milky Way, along with thousands of other galaxies, is falling toward it at more than 600 kilometers per second. Beyond the Great Attractor is an even larger structure, the Shapley supercluster, and beyond that, something else, pulling everything in that direction. We have mapped the flow of galaxies across vast distances, and the pattern suggests that there is more mass in the universe than we have accounted for, more structure than we have observed. Dark matter is the term we use for the mass we cannot see. It does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. We know it exists because galaxies rotate too quickly to be held together by visible matter alone. We know it exists because clusters of galaxies bend light in ways that require far more mass than we can observe. We know it exists because the cosmic microwave background requires it to match our observations. Dark matter makes up roughly 85% of all matter in the universe. We do not know what it is. We have never detected a dark matter particle. We have built detectors deep underground, shielded from cosmic rays, waiting for the faint collision of a dark matter particle with an ordinary atom. We have found nothing. We have searched for dark matter at particle accelerators, smashing protons together at nearly the speed of light, hoping to create dark matter particles in the debris. We have found nothing. Dark matter remains invisible, theoretical, necessary, and absent. But what if dark matter is not a particle? What if it is a field, a distortion in space itself, a relic of a previous state of existence? What if the structures we see, the filaments and voids, the flows and attractors, are not the result of gravity acting on matter over billions of years, but the remnants of patterns that existed before the Big Bang, imprinted on space like scars on skin? There is a model called conformal cyclic cosmology, proposed by physicist Roger Penrose. It suggests that the universe undergoes infinite cycles. Each cycle begins with a Big Bang and ends in a state of maximum entropy, a cold, empty expanse where all matter has decayed and only radiation remains. But in that far future, when there is no matter left, only massless particles, the concept of time becomes meaningless. Massless particles do not experience time. From their perspective, the end of one universe and the beginning of the next are the same event. The Big Bang of the next cycle is the infinite future of the previous one. If this model is correct, then the universe we observe is not the first. It is one in an endless chain, and the structures we see, the anomalies in the cosmic microwave background, the unexpected alignments, could be echoes of the previous universe, signals that survive the transition. Penrose has claimed to find evidence of this in the cosmic microwave background. He has identified circular patterns, rings of slightly different temperature, which he interprets as the signatures of supermassive black hole collisions from the previous universe. These rings, if real, will be the oldest evidence we have of anything older than time itself. Other scientists have analyzed the same data and found nothing. They argue that the patterns are random noise, artifacts of how we process the data, the result of searching for patterns in randomness until something appears. The debate continues. The data is public. Anyone can examine it. But interpretation is not neutral. What one person sees as a signal, another sees as static. Then there are the objects that do not belong. In 2017, an object entered our solar system from interstellar space. It was small, a few hundred meters long, tumbling end over end. We named it Oumuamua, a Hawaiian word meaning scout. It was the first confirmed interstellar object we had ever detected. Its trajectory was unusual. It came from the direction of the star Vega, but Vega was not in that position when Oumuamua began its journey. It had been traveling for millions of years. As it passed the sun, it accelerated slightly, faster than gravity alone would predict. This is not unheard of. Comets do this. When they approach the sun, ice on their surface vaporizes, creating jets of gas that push them off course. But Oumuamua showed no signs of outgassing. No tal, no coma, no gas, just acceleration. Some scientists proposed that it was a comet with an unusual composition, ice that vaporizes without leaving visible traces. Others suggested it was a solid object, tumbling in such a way that sunlight pushed it, a phenomenon called radiation pressure. But for radiation pressure to produce the observed acceleration, Oumuamua would have to be extraordinarily thin, shaped like a pancake or a sail, less than a millimeter thick. No natural process we know of creates objects like that. One scientist, Avi Loeb, suggested that it could be artificial, a piece of technology, a light sail from another civilization. This was met with skepticism. The scientific community prefers natural explanations. But no natural explanation fits all the data. Oumuamua remains unexplained. 2 years later, another interstellar object entered the solar system. This one, named Borisov, behaved exactly like a comet. It had a tail. It outgassed. It followed predictable physics. Borisov was normal. Oumuamua was not. We will never see Oumuamua again. It has left the solar system, accelerating into the darkness, and we do not have the technology to follow it. But its visit raised a question. If interstellar objects pass through our solar system regularly, and if some of them are unusual, then what else is out there? What else have we missed? The universe is expanding, and that expansion is accelerating. This was discovered in 1998 when astronomers measured the light from distant supernovae and found that they were dimmer than expected. Dimmer light means greater distance. Greater distance means the universe is expanding faster now than it was in the past. This should not happen. Gravity should slow the expansion. The combined mass of all matter in the universe, visible and dark, should act as a brake, pulling everything back together. But instead, the expansion is speeding up. Something is pushing space apart. We call this dark energy, and it makes up roughly 68% of the total energy of the universe. We do not know what it is. We do not know where it comes from. We do not know if it is a property of space itself or a field permeating space. The simplest explanation is that dark energy is the cosmological constant, a term Albert Einstein added to his equations of general relativity and later called his greatest blunder. The cosmological constant represents the energy of empty space, the vacuum energy, and in quantum field theory, this energy should be enormous. But when we calculate its value, we get a number that is 10 to the power of 120 times larger than what we observe. This is the worst prediction in the history of physics. We are off by more than 100 orders of magnitude. Something is canceling out the vacuum energy, reducing it to the tiny value we measure, and we have no idea what. If dark energy is real, and if it continues to accelerate the expansion, then the universe will eventually be torn apart. Galaxies will move away from each other faster than light can travel between them. Stars will blink out one by one, their light redshifted into invisibility. Eventually, even atoms will be ripped apart, their electrons stripped away, their nuclei dissolved. This is called the Big Rip, and it is one possible end of the universe. But it is not the only one. Another possibility is heat death. The universe continues to expand, but not violently. Stars exhaust their fuel and go dark. Galaxies fade. Black holes evaporate through Hawking radiation, a slow process that takes 10 to the power of 100 years. Eventually, all matter decays, all energy disperses, and the universe becomes a uniform, cold, empty expanse at a temperature just above absolute zero. Nothing happens anymore. Time loses meaning. This is maximum entropy, the state of ultimate disorder, and it is irreversible, unless it is not. Entropy is the measure of disorder, and the second law of thermodynamics states that entropy always increases. This is why time has a direction. This is why we remember the past, but not the future. This is why eggs break, but do not unbreak, why ice melts, but does not unmelt. Entropy is the arrow of time. But the laws of physics, at their most fundamental level, are time-symmetric. The equations work just as well forward as backward. There is nothing in quantum mechanics or general relativity that prefers one direction of time over another. The arrow of time emerges from entropy, from the fact that the universe began in a low-entropy state and has been increasing in entropy ever since. But why did the universe begin in a low-entropy state? Why was the Big Bang so ordered, so smooth, so uniform? A random beginning should have been chaotic, high entropy, and such a universe would have no structure, no stars, no life. The low-entropy beginning is one of the deepest mysteries in cosmology, and it suggests that the Big Bang was not random. It was prepared. There is a hypothesis called cosmological natural selection, proposed by physicist Lee Smolin. It suggests that universes reproduce. When a black hole forms in our universe, it collapses into a singularity, and on the other side of that singularity, a new universe is born. This new universe inherits properties from the parent universe, but with slight variations, like mutations in biology. Over time, universes that are good at producing black holes become more common, because they produce more offspring. Our universe is good at producing black holes. It has stars, and stars create black holes when they die. It has the right balance of physical constants to allow stars to form. If the strength of gravity were slightly different, or if the nuclear forces were slightly weaker, stars would not exist, black holes would not form, and such a universe would have no descendants. We exist in a universe that is fine-tuned for black hole production, not because we are special, but because we are descended from a long line of universes that share this property. This model makes no predictions. It cannot be tested, but it provides a possible answer to the question of why the universe has the properties it does. We are not the first universe. We are the product of trillions of generations of universes, each one slightly different, each one selected for its ability to create the next. And if this is true, then the structures we see, the dark matter, the dark energy, the anomalies in the cosmic microwave background could be inherited traits, features passed down from previous universes, adaptations that helped our ancestors survive and reproduce. But there is another interpretation, one that is less optimistic. What if the anomalies are not inherited? What if they are intrusions? What if something from outside our universe, or from before a universe, is leaking through? There is a concept in quantum field theory called vacuum decay. The vacuum of space is not truly empty. It is filled with fields, and those fields have energy. But the vacuum we observe may not be the lowest energy state possible. It may be a false vacuum, stable for now, but not forever. If the vacuum is false, then it could decay into a true vacuum, a state of lower energy, and when that happens, a bubble of true vacuum would form and expand at the speed of light, destroying everything it touches. Inside the bubble, the laws of physics would be different. Particles would have different masses. Forces would have different strengths. Atoms could not exist. The decay of the vacuum would be the end of everything, and there would be no warning. Some physicists believe this has already happened. They believe our universe is the bubble, the region of decayed vacuum, and the space outside our observable universe is still in the false vacuum state. The Big Bang was not the beginning of everything. It was the beginning of the decay, the moment when the bubble formed. And if that is true, then the edge of our observable universe is not a horizon. It is a boundary, the wall of the bubble, expanding outward, converting false vacuum into true vacuum, rewriting reality as it goes. We cannot see beyond the boundary, because light from outside has not had time to reach us. But we can see the effects. The cosmic microwave background, the afterglow of the Big Bang, is not the radiation from the initial explosion. It is the radiation from the boundary, the light emitted as the false vacuum decayed. The fluctuations in the background, the hot and cold spots, are not quantum fluctuations stretched by inflation. They are interference patterns, the result of the bubble interacting with the structure of the false vacuum outside. This interpretation is speculative. It is not widely accepted, but fits the data. It explains why the cosmic microwave background has anomalies. It explains why the universe is so flat, so uniform. It explains why inflation seems fine-tuned to produce a universe like ours. And it suggests that the universe we observe is not the whole story. It is a local phenomenon, a bubble in a larger structure, and that larger structure has been there all along, older than time, waiting. The horizon problem is one of the puzzles that inflation was designed to solve. When we look at the cosmic microwave background, we see that it is almost exactly the same temperature in every direction. But regions on opposite sides of the sky are so far apart that light has not had time to travel between them since the Big Bang. They should never have been in contact. They should have different temperatures, different properties. But they do not. They are nearly identical. Inflation solves this by proposing that the universe was once much smaller, small enough for all regions to be in contact, and then it expanded so rapidly that those regions were pushed far apart. But inflation requires precise initial conditions. The inflatant field, the hypothetical field that drove inflation, must have had almost exactly the right energy density, the right rate of decay. If it had been slightly different, inflation would have ended too soon or lasted too long, and we would not have a universe capable of forming stars and galaxies. This is called the fine-tuning problem, and it is one of the reasons some physicists are uncomfortable with inflation. The theory solves one problem by introducing another. It replaces one set of unlikely initial conditions with a different set of unlikely initial conditions. And it raises the question, if the inflatant field had to be fine-tuned, what fine-tuned it? One answer is that we are observing selection bias. In a multiverse, where every possible outcome happens somewhere, we naturally find ourselves in a universe that is capable of supporting observers. We do not find ourselves in a universe where inflation failed or where stars never formed, because such universes have no one to observe them. This is called the anthropic principle, and it is not an explanation. It is an acknowledgement that some questions may not have answers, that the universe may not be the way it is for any reason at all. But there is another answer, one that requires us to abandon the idea that the Big Bang was the beginning. If the Big Bang was not the beginning, then the initial conditions were not random. They were the result of a previous process, something that shaped space and time before a universe existed. That process could have been another universe, collapsing and rebounding. It could have been a collision between membranes in higher dimensional space, as suggested by string theory. It could have been a quantum tunneling event, where a small region of space spontaneously transitioned from one state to another. Whatever it was, it left a mark, and that mark is what we observe. The Hubble tension is another crack in the foundation. The Hubble constant measures the rate of expansion of the universe, how fast galaxies are moving away from each other. We can measure this in two ways. One way is to observe distant supernovae and calculate their distances and velocities. The other way is to analyze the cosmic microwave background and use our models of the early universe to predict the current expansion rate. These two methods should give the same answer. They do not. The value from supernovae is about 10% higher than the value from the cosmic microwave background. This discrepancy is called the Hubble tension, and it has persisted for years. At first, it was thought to be a measurement error, a problem with the instruments or the analysis. But as measurements have improved, the discrepancy has not disappeared. It has become more significant. One explanation is that our model of the universe is incomplete. Perhaps dark energy is not constant. Perhaps it changes over time. Perhaps there is an additional component to the universe, something we have not accounted for. Another explanation is that the early universe was different than we think. Perhaps inflation did not happen the way we assume. Perhaps the cosmic microwave background is not telling us what we think it is telling us. Or perhaps the two measurements are both correct, and the expansion rate of the universe has changed in ways we do not understand. There is also the possibility that the Hubble tension is evidence of a phase transition, a change in the fundamental properties of space that occurred sometime after the cosmic microwave background was emitted. If space itself changed, if the vacuum decayed from one state to another, then the expansion rate measured from the cosmic microwave background would not match the expansion rate we measure today. the universe would have undergone a shift, and we are living in the aftermath. We have detected signals that do not fit. Radio telescopes scanning the sky occasionally pick up bursts of energy, brief pulses of radio waves that last only milliseconds. These are called fast radio bursts, and their origin is unknown. Some repeat, some do not. Some come from galaxies billions of light years away. Others have no identified source. The energy required to produce these bursts is enormous, equivalent to the sun's output over an entire day, released in a fraction of a second. No known process should create such bursts. Neutron stars can produce radio waves. Supermassive black holes can produce radio waves, but neither produces the short, intense bursts we observe. One hypothesis is that fast radio bursts are caused by magnetars, neutron stars with extraordinarily powerful magnetic fields. When the crust of a magnetar cracks, it releases energy in a violent eruption, and some of that energy could be channeled into a radio burst. This explanation works for some bursts, but not all. Some bursts are too energetic. Some come from regions with no neutron stars. Some repeat in patterns that suggest a regular process, not a random eruption. The mystery remains. Another mystery is the cosmic radio background, a faint hum of radio waves that fills the universe. It is similar to the cosmic microwave background, but at longer wavelengths. We expect this background to come from distant galaxies, from radio-emitting stars and black holes. But when we subtract all known sources, the residual signal remains stronger than it should be. The excess is small, barely detectable, but it is there. Some scientists believe it is an error, a calibration issue with the instruments. Others believe it is real, evidence of a population of objects or events we have not yet identified. And a few have suggested that it could be a relic, a signal from the early universe, or from before the universe, a remnant of whatever existed before the Big Bang. We have also found anomalies in the distribution of matter. The universe, at the largest scales, should be smooth. Galaxies should be spread evenly, with small fluctuations. But when we map the positions of galaxies across vast distances, we find that they are arranged in patterns. Not random patterns, organized patterns. Filaments and walls, voids and clusters, repeating at scales that seem too large to be the result of random chance. This is the cosmic web, the largest known structure in the universe, and it is beautiful and unsettling. The cosmic web forms because of gravity. Dark matter clumps, and ordinary matter follows. Over billions of years, small clumps merge into larger clumps, and galaxies form along the filaments where dark matter is densest. This process is well understood, and our simulations reproduce the basic structure of the cosmic web. But the simulations do not capture everything. They do not explain why some filaments are so long, so straight, so uniform. They do not explain why some voids are so empty, so perfectly spherical. And they do not explain why the cosmic web, when viewed at the largest scales, seems to have a texture, a grain, as if space itself has been stretched along certain directions. There is a feature in the cosmic microwave background called a cold spot. It is a region about 10 degrees across, significantly colder than the surrounding area. Cold spots should exist. The cosmic microwave background is not perfectly smooth, but this cold spot is larger and colder than our models predict. One explanation is that it is a statistical fluke, a rare but possible outcome of random fluctuations. Another explanation is that it is the result of a supervoid, an enormous region of space with less matter than average. Light traveling through a void loses energy and arrives at us colder. This is called the integrated Sachs-Wolf effect, and it can produce cold spots. But the void required to explain the cold spot would have to be extraordinarily large, larger than any void we have observed, and it is not clear that such a void exists in that direction. A third explanation is more exotic. Some physicists have proposed that the cold spot is a scar, the result of a collision between our universe and another universe. In the multiverse, bubbles of space occasionally touch, and when they do, they leave marks on each other. The cold spot, in this interpretation, is the imprint of another universe, evidence that we are not alone, that the Big Bang was not the creation of everything, but the creation of one bubble among many. This explanation is speculative. It is untestable, but is not impossible. We have also found patterns in the polarization of the cosmic microwave background. Light can be polarized, meaning its waves oscillate in a preferred direction. The cosmic microwave background is polarized because the photons scattered off electrons in the early universe, and the scattering process created a pattern. This pattern is predicted by our models, and it matches the observations. But there are anomalies. Some regions have stronger polarization than expected. Others have weaker, and in some regions, the direction of polarization aligns in ways that seem non-random, as if the early universe had a preferred orientation. These anomalies are subtle. They are not obvious violations of the models. They are deviations, small enough to be consistent with statistical noise, but persistent enough to make some scientists uncomfortable. And when small deviations accumulate, when multiple independent anomalies all point in the same direction, it becomes harder to dismiss them as coincidence. The standard model of cosmology is called lambda CDM. Lambda represents dark energy, the cosmological constant. CDM stands for cold, dark matter, the invisible mass that holds galaxies together. Lambda CDM is extraordinarily successful. It explains the cosmic microwave background. It explains the distribution of galaxies. It explains the expansion of the universe. It has been tested against decades of observations, and it passes every test. But it is not perfect. It has anomalies. It has tensions, and it requires two components, dark matter and dark energy, that we have never directly detected and do not understand. Some physicists believe lambda CDM is incomplete, a good approximation, but not the final answer. Others believe it is fundamentally correct, and the anomalies will eventually be resolved with better data or refined models. But there's a third group, smaller and quieter, that believes the anomalies are telling us something important, that the universe is not what we think it is, that the Big Bang was not the beginning. Time is a dimension like space, but it is different. We can move through space in any direction, forward or backward, left or right, up or down. But we can only move through time in one direction, from past to future. This asymmetry is not explained by the fundamental laws of physics. The equations of quantum mechanics and general relativity work equally well in both directions. The arrow of time is not written into the laws. It emerges from the initial conditions, from the fact that the universe began in a low-entropy state. But why did it begin that way? Why was the Big Bang so ordered? In a random universe, entropy should be high. The initial state should be chaotic, a uniform soup of energy with no structure. But the Big Bang was not chaotic. It was smooth, nearly uniform, with only tiny fluctuations. This is one of the most profound puzzles in cosmology, and it has no agreed-upon answer. One possibility is that the Big Bang was not the beginning. It was a transition, a moment when the universe changed from one state to another, and the low-entropy state we observe is a remnant of whatever came before. If the previous state was even lower in entropy, then the Big Bang would represent an increase in entropy, consistent with the second law of thermodynamics. But this pushes the problem back. Where did the previous state come from? How is it so ordered? The chain of causation seems to extend infinitely into the past, with no origin, no first cause. Another possibility is that entropy is not fundamental. Perhaps there is a deeper principle, something underlying thermodynamics that determines the arrow of time. Perhaps time itself is not fundamental, but an emergent property, something that arises from more basic processes. This is the domain of quantum gravity, the attempt to unify quantum mechanics and general relativity into a single theory. In quantum gravity, space and time are not fixed backgrounds. They're dynamic, woven together, shaped by energy and matter. And at the smallest scales, at the Planck length, 10 to the negative 35 meters, space and time may not exist as smooth, continuous dimensions. They may be discrete, granular, a foam of fluctuating geometry. If space and time are emergent, then the Big Bang is not a moment in time. It is a transition between two regimes, one where time exists and one where it does not. Before the Big Bang, there was no before because time had not yet emerged. The question of what existed before the universe is meaningless, like asking what is north of the North Pole. But even if time did not exist, something must have existed. The laws of physics, or the potential for the laws of physics, or the mathematical structure that gives rise to the laws of physics, must have been there, waiting. We have observed distant galaxies that appear to be rotating in coordinated patterns. This should not happen. Galaxies form independently from separate clouds of gas and dark matter. Their rotations should be random, uncorrelated. But in some regions of the sky, galaxies seem to spin in the same direction, as if they were part of a larger structure, influenced by a common process. This phenomenon is called angular momentum alignment, and it has been reported in multiple studies. Some scientists argue that the effect is weak, that the alignments are marginal and could be explained by selection bias or systematic errors in the data. Others believe the effect is real, and that it indicates a large-scale structure or field that influenced the formation of galaxies across vast distances. If the alignment is real, it could be evidence of a primordial magnetic field, a weak magnetic field that filled the early universe and left an imprint on the distribution of matter. Or it could be evidence of cosmic strings, hypothetical one-dimensional defects in space, remnants of a phase transition in the early universe. Or it could be something else, something we have not yet imagined. We have also detected anomalies in the distribution of gamma-ray bursts, the most energetic explosions in the universe. Gamma-ray bursts occur when massive stars collapse into black holes or when neutron stars collide. They release more energy in a few seconds than the sun will emit over its entire lifetime. They are visible across the entire observable universe. When we map their positions, we expect them to be spread randomly across the sky, because the events that cause them are random. But some studies have found that gamma-ray bursts are not distributed randomly. They cluster in certain regions and avoid others, as if the universe has a preferred structure at the largest scales. This clustering is controversial. Some scientists believe it is real. Others believe it is an artifact of how we detect gamma-ray bursts, a bias introduced by the instruments or the data analysis. The debate continues, but the possibility remains that the universe is not isotropic, not the same in every direction, and that the Big Bang did not erase all traces of what came before. There's a concept in physics called the holographic principle. It suggests that the information contained in a volume of space can be encoded on the boundary of that space, on a surface with one fewer dimension. This principle comes from the study of black holes. When matter falls into a black hole, it seems to disappear, taking its information with it. But information cannot be destroyed, according to quantum mechanics. The solution is that the information is not lost. It is stored on the event horizon, the surface of the black hole, encoded in a two-dimensional pattern. The interior of the black hole, the three-dimensional volume, is a projection of that two-dimensional surface. If the holographic principle is true for black holes, it may be true for the universe. The entire universe, with all its galaxies, stars, and planets, may be a projection from a distant boundary, a surface at the edge of space. We experience three dimensions, but the fundamental reality may be two-dimensional, and everything we perceive is a hologram, a shadow cast by information on the boundary. This idea is strange, but it is taken seriously by physicists working on quantum gravity. It provides a way to reconcile the paradoxes of black holes with the laws of quantum mechanics. And it suggests that the structure of space is not what it seems, that the universe is more like a computation than a physical object, and that what we observe is the output of a process happening elsewhere, on a boundary we cannot see. If the universe is a hologram, then the Big Bang is not the creation of space. It is the initialization of the computation, the moment when the program began to run. And the anomalies we observe The patterns in the cosmic microwave background, the alignments, the clustering could be artifacts of the encoding, glitches in the projection, evidence that the hologram is not perfect. We have sent probes to the edge of the solar system, and they have behaved strangely. The Pioneer probes, launched in the 1970s, experienced an unexplained deceleration, a tiny force pushing them back toward the sun. The force was small, about 10 to the negative 10 meters per second squared, but it was consistent and measurable. For years, scientists debated its cause. Some suggested it was thermal radiation, heat leaking from the probe's power sources, creating an asymmetric thrust. Others proposed that it was a gravitational anomaly, evidence that our understanding of gravity is incomplete. Eventually, the thermal explanation was accepted, but not before the Pioneer anomaly sparked discussions about the possibility that physics behaves differently at the edge of the solar system, far from the sun's gravitational influence. The Voyager probes, also launched in the 1970s, have crossed the boundary of the heliosphere, the bubble of charged particles blown outward by the solar wind. Beyond the heliosphere is interstellar space, the region between stars, filled with gas and cosmic rays from distant supernovae. The Voyager probes have sent back data from this region, and the data is surprising. The density of interstellar gas is higher than expected. The magnetic field is stronger than expected. And there are structures in the data, patterns that suggest the interstellar medium is not uniform, that has been shaped by processes we do not fully understand. One of those processes could be the movement of the solar system through the galaxy. The sun orbits the center of the Milky Way, and as it moves, it plows through clouds of gas and dust. These clouds have different densities, different compositions, different magnetic fields. When the solar system enters a new cloud, the properties of interstellar space change, and those changes affect the heliosphere, the solar wind, and potentially the climate of the planets. We have evidence that the solar system has passed through denser regions in the past, and that those passages may have influenced the history of life on Earth. But there is another possibility, one that is more speculative. The interstellar medium may not be shaped only by the motion of stars and the remnants of supernovae. It may also be shaped by the structure of space itself, by the distribution of dark matter, by the flow of energy through the galaxy. And if that is true, then the patterns we observe in the interstellar medium could be echoes of a larger structure, a galactic-scale network of dark matter filaments and voids, a web that connects the stars and determines their motion. The Milky Way is not isolated. It is part of a group of galaxies called the Local Group, which includes the Andromeda Galaxy and about 50 smaller galaxies. The Local Group is itself part of a larger structure, the Virgo supercluster, which contains thousands of galaxies spread across tens of millions of light years. And the Virgo supercluster is part of an even larger structure, the Laniakea supercluster, which contains 100,000 galaxies and spans 500 million light years. We are embedded in a hierarchy of structures, each one larger and older than the last. And at every scale, we find patterns. These patterns are not random. They are the result of gravity, acting over billions of years, pulling matter together into filaments and clusters, leaving voids where matter has been pulled away. But the patterns are also the result of the initial conditions, the fluctuations in the cosmic microwave background, the seeds of structure planted in the first moments after the Big Bang. And those seeds, those fluctuations, were shaped by inflation or by whatever process came before inflation, and that process may have been influenced by something older still. The question is not whether the universe had a beginning. The question is whether that beginning was the first beginning, or whether it was the continuation of something that already existed. There are physicists who believe the universe is eternal, that it has no beginning and no end, that the Big Bang was not the creation of space and time, but a phase transition, a change of state, like water freezing into ice or boiling into steam. In this view, the universe undergoes cycles, expanding and contracting, heating and cooling, dying and being reborn. Each cycle is different, with different properties, different structures, but the underlying fabric of space and time is continuous, unbroken, eternal. This model avoids the problem of the initial singularity, the point at the beginning of the Big Bang, where the equations of general relativity break down and give nonsensical answers. In a cyclic universe, there is no singularity. The universe contracts, but it does not collapse to a point. It reaches a minimum size, and then it bounces, expanding again into a new cycle. The bounce is controlled by quantum effects, by the uncertainty principle, which prevents space from collapsing to zero volume. The cyclic model makes predictions. It predicts that the cosmic microwave background should have specific patterns, signatures of the bounce, imprints of the previous cycle. Some scientists have searched for these signatures and found nothing. Others have found hints, anomalies that could be consistent with a bounce. The data is not conclusive. The model is not proven, but it remains a possibility, a framework for understanding the universe that does not require a beginning. Another framework is string theory, the attempt to describe all particles and forces as vibrations of tiny strings, one-dimensional objects smaller than atoms, smaller than protons, smaller than anything we can measure. In string theory, space has more than 3 dimensions. It has 10 or 11, depending on the version of the theory. The extra dimensions are curled up, compactified, hidden from view at scales too small for our instruments to detect. The shape of these extra dimensions determines the properties of the particles we observe, the masses, the charges, the forces. Different shapes produce different physics. String theory allows for the existence of branes, higher dimensional objects that extend through some of the extra dimensions. Our universe could be a brane, a 3-dimensional surface embedded in a higher dimensional space. Other branes could exist nearby, separated by a tiny distance in the extra dimensions, invisible to us because light and matter are confined to our brain. But gravity is not confined. Gravity can propagate through the extra dimensions, and if 2 branes come close enough, they can interact. They can collide. A collision between branes would release an enormous amount of energy, enough to create a Big Bang. In this scenario, the Big Bang was not the beginning of everything. It was the result of a collision between our brane and another brane, and the energy from the collision is what we observe as the cosmic microwave background. Before the collision, the branes existed empty or filled with different matter, and after the collision, our universe began. This model is called the ekpyrotic scenario, and it has implications. If branes can collide once, they can collide again. The collision could be periodic, repeating every trillion years, or it could be random, triggered by fluctuations in the higher dimensional space. Either way, the universe we observe is not unique. It is one event in a sequence, and there were events before it, and there will be events after it. The ekpyrotic scenario predicts specific patterns in the cosmic microwave background, different from the patterns predicted by inflation. Observations so far favor inflation, but the data is not precise enough to rule out the ekpyrotic model. Both remain possible. Both suggest that the Big Bang was not the beginning. We have measured the curvature of space, and we have found that it is flat, or very nearly flat. This means that parallel lines remain parallel, that the angles of a triangle add up to 180 degrees, that space follows the rules of Euclidean geometry. But flatness is unstable. A universe that is slightly curved will become more curved as it expands, unless something counteracts the curvature. Inflation counteracts the curvature by expanding the universe so rapidly that any initial curvature is smoothed out, stretched flat. But this requires that the universe was flat to begin with, or very nearly flat, and that is another fine-tuning problem. The flatness we observe is also evidence that the universe is larger than what we can see. The observable universe is finite, bounded by the distance light has traveled since the Big Bang. Beyond that distance, space continues, but we cannot observe it. If space is flat, then the total size of the universe is likely much larger than the observable part, possibly infinite. And if the universe is infinite, then every possible arrangement of matter exists somewhere. There are infinite copies of Earth, infinite copies of you, living in regions of space so far away that their light will never reach us. This is called the infinite universe hypothesis, and it is not a fringe idea. It is a straightforward consequence of the equations. If space is flat and extends forever, but infinity is uncomfortable, it raises questions about probability, about identity, about what it means to be unique. If there are infinite copies of you, are you the same person? If every possible event happens somewhere, does probability lose its meaning? And if the universe is infinite, how do we define the Big Bang? Did it happen everywhere at once? Or did it start in one place and spread? The answer depends on how we interpret the equations, and there is no consensus. We have also measured the temperature of space, the temperature of the cosmic microwave background, and we have found that it is 2.7 Kelvin, just above absolute zero. This is cold, but it is not as cold as it could be. The universe has cooled as it expanded, and it will continue to cool, but it will never reach absolute zero because the expansion will never stop. Dark energy ensures that. As long as dark energy exists, the universe will expand forever, and the temperature will approach zero asymptotically, getting closer and closer, but never quite reaching it. But what if dark energy is not constant? What if it changes over time, growing stronger or weaker? If dark energy grows stronger, the expansion will accelerate faster, and the universe will end in a big rip torn apart by the increasing force. If dark energy grows weaker, the expansion could slow down, stop, and reverse, leading to a big crunch, where the universe collapses back into a singularity. And if dark energy can change, then it may have been different in the past, different in the early universe, and that difference could have left a mark, a signature in the cosmic microwave background or the distribution of galaxies. Some scientists have searched for evidence of changing dark energy and found none. Others have found hints, small deviations in the data that could be consistent with a changing cosmological constant. The evidence is not strong. The hints are not definitive, but they are there, and they raise the possibility that the universe is more dynamic than we think, that the forces shaping it are not fixed, that the future is not determined. There is also the question of the cosmological constant problem. Why is dark energy so small? In quantum field theory, the vacuum should have energy, and that energy should be enormous, far larger than what we observe. But it is not. The vacuum energy is small, just barely enough to cause the universe to accelerate. This fine-tuning is even more extreme than the fine-tuning of inflation, and it suggests that something is regulating the vacuum energy, keeping it at a precise value. But we do not know what. One proposal is that the vacuum energy is canceled by a symmetry, a hidden relationship between particles and forces that causes positive and negative contributions to balance. This symmetry is called supersymmetry, and it predicts the existence of new particles, partners to the particles we know, with slightly different properties. Experiments at particle accelerators have searched for these supersymmetric particles and found nothing. The simplest versions of supersymmetry have been ruled out. More complex versions remain possible, but they require increasingly contrived parameters, and many physicists have lost faith in the idea. Another proposal is that the vacuum energy is not fine-tuned. It is selected. In a multiverse, where every possible value of the cosmological constant exists somewhere, we naturally find ourselves in a universe where the value is small enough to allow galaxies and stars to form. If the cosmological constant were much larger, the universe would expand too quickly for structure to form. If it were negative, the universe would collapse before stars could ignite. We observe a small positive value because that is the only type of universe where observers can exist. This is the anthropic explanation, and it is deeply unsatisfying to many scientists because it replaces prediction with selection, explanation with observation. But the anthropic explanation may be correct. It may be that the universe is not the way it is for any reason, that the constants of nature are not determined by a deeper principle, that we are simply one outcome among many, lucky to exist in a universe that allows life. And if that is true, then the search for a final theory, a unified explanation for all the forces and particles, may be futile. There may be no final theory. There may only be a landscape of possibilities, and we are in one small corner of that landscape, looking out at the others, unable to reach them. We have detected something called the dipole repeller, a region of space that is pushing galaxies away. This is the opposite of an attractor. Instead of pulling matter toward it, it is pushing matter away, creating a flow, a current of galaxies moving in a specific direction. The dipole repeller is not a single object. It is a vast void, a region where matter is sparse, and its gravitational effect is repulsive. Gravity pulls, but the absence of gravity also has an effect. When one region has more matter and another has less, the difference creates a flow, and that flow can be measured. The discovery of the dipole repeller has refined our understanding of the local universe, the motion of galaxies within a few 100 million light years, but has also raised questions. How did such a large void form? Why is it so empty? And why does the flow of galaxies align with the direction of the great attractor, as if the two structures are connected, part of a larger pattern? The pattern extends beyond the local universe. When we map the distribution of galaxies across billions of light years, we see that they are not randomly scattered. They are organized into a network, a cosmic web, and the web has a structure, a geometry, that is determined by the initial conditions of the universe, the fluctuations in the cosmic microwave background. But the geometry is also influenced by the expansion of space, by the action of dark energy, by the flow of matter over time. And that flow, that motion, carries information about the past, about the forces that shape the universe, about the events that occurred before the Big Bang, if such events existed. We have also found evidence of cosmic flows on even larger scales, bulk flows, where large numbers of galaxies are moving in the same direction at velocities that cannot be explained by the matter we observe. These flows suggest the presence of mass beyond our observable horizon, structures so distant that their light has not yet reached us, but whose gravitational influence extends into our region of space. This is consistent with the idea that the observable universe is a small part of a much larger structure, that the Big Bang was a local event, and that the full extent of reality is beyond our ability to measure. But it is also unsettling, because it means that we are influenced by things we cannot see, that the motion of our galaxy, the formation of our solar system, the evolution of life on Earth, are all shaped by forces that originate beyond the edge of the observable universe, in regions that are forever inaccessible to us. We are not isolated. We are embedded in a larger structure, and that structure has a history that extends beyond the 13.8 billion years we call the age of the universe. The cosmic neutrino background is a sea of particles that fills the universe, left over from the Big Bang. Neutrinos are nearly massless particles that interact very weakly with matter. They pass through planets, stars, and galaxies almost without noticing them. Billions of neutrinos pass through your body every second, remnants of the Big Bang, and you do not feel them. The cosmic neutrino background is similar to the cosmic microwave background, but it is much harder to detect because neutrinos interact so weakly. We have not yet directly observed the cosmic neutrino background, but we know it exists because the equations predict it, and the equations have been confirmed by every other observation. If we could detect the cosmic neutrino background, we could learn about the universe in the first second after the Big Bang, a time when the universe was too hot and dense for light to escape. The cosmic microwave background shows us the universe as it was 380,000 years after the Big Bang, when it became transparent. The cosmic neutrino background would show us the universe as it was 1 second after the Big Bang, when neutrinos decoupled from matter and began to travel freely. This is a much earlier snapshot, and it would tell us about conditions we cannot currently observe. But there is also the possibility that the cosmic neutrino background contains anomalies, patterns that do not match the predictions, evidence of processes that occurred before the Big Bang. Neutrinos, like photons, carry information about the state of the universe at the time they were created. If the early universe was not perfectly smooth, if it had structures or fields that influenced the distribution of neutrinos, then those structures would leave an imprint, and that imprint could be detected, if we had sensitive enough instruments. We do not have those instruments yet. Detecting the cosmic neutrino background is one of the most challenging problems in experimental physics, but is not impossible. Projects are being planned, techniques are being developed, and in the coming decades, we may finally observe the neutrino background. And when we do, we will learn whether the early universe was as smooth and simple as we think, or whether it carried the scars of something older. We have found objects that do not decay. In the quantum world, particles are constantly fluctuating, appearing and disappearing, borrowing energy from the vacuum and paying it back. This is allowed by the uncertainty principle, which states that energy and time cannot both be measured precisely. Over very short timescales, energy conservation can be violated, and particles can exist temporarily, virtual particles popping into and out of existence. These virtual particles have real effects. They contribute to the forces between particles. They affect the behavior of atoms. They're the reason that the vacuum is not truly empty. But there are also particles that do not decay, that are stable, that last forever. Protons are one example. As far as we know, protons do not decay. They are stable, and they will exist for trillions of years, possibly forever. But some theories predict that protons should decay, very slowly, over timescales longer than the current age of the universe. Experiments have been built to detect proton decay, deep underground, shielded from cosmic rays, watching enormous tanks of water for the flash of light that would signal the disintegration of a proton. No decay has been observed. Protons, it seems, are truly stable. But if protons are stable, then matter is eternal. The atoms in your body will exist forever, or at least for as long as the universe exists. They will not decay. They will not disappear. They will eventually be dispersed, scattered across space as stars die and galaxies evaporate, but they will still be there, drifting through the void, unchanged. This is both comforting and disturbing. Comforting because it means that nothing is truly lost. Disturbing because it means that the universe will never be completely empty, never truly at rest. There will always be remnants, traces of the past, particles that remember what came before. We have also found that black holes are not truly black. They emit radiation, Hawking radiation, a faint glow caused by quantum effects near the event horizon. Virtual particles appear in pairs near the horizon, one with positive energy and one with negative energy. Normally, they would annihilate each other and disappear. But near a black hole, one particle can fall in, carrying negative energy, while the other escapes, carrying positive energy. The escaping particle is real, and it carries energy away from the black hole. The black hole loses mass. Over an unimaginably long time, longer than the current age of the universe by many orders of magnitude, the black hole evaporates, shrinks, and eventually disappears in a final burst of radiation. When a black hole evaporates, what happens to the information it contained? Everything that fell into the black hole, every particle, every photon, every bit of data, seems to be lost. But quantum mechanics says that information cannot be destroyed. This is the black hole information paradox, and it has troubled physicists for decades. Some believe that the information is not lost, that it is somehow encoded in the Hawking radiation, scrambled but recoverable. Others believe that the information is stored on the event horizon, consistent with the holographic principle. And a few have suggested that the information escapes into another universe, through a wormhole or a tunnel in space, and that black holes are gateways to regions of space we cannot observe. If black holes are gateways, then they could connect our universe to other universes or to other regions of our own universe, far beyond the observable horizon. Matter and energy that fall into a black hole in our region could emerge from a white hole in another region, creating a flow, a circulation of matter through space. This would make the universe more connected than we think, more dynamic, more alive. And it would mean that the structures we observe, the galaxies and clusters, are not isolated. They are nodes in a network, connected by black holes, linked by flows of matter and energy that we cannot see. But this is speculation. We have no evidence of white holes. We have no evidence of matter emerging from black holes. The mathematics allows for it, but mathematics allows for many things that do not exist. The universe is under no obligation to be as interesting as our equations suggest. We have also discovered that space is not empty. Even in the darkest voids, far from galaxies, far from stars, there is something. There is the cosmic microwave background, filling every direction with faint light. There are neutrinos streaming through space, relics of the Big Bang. There is dark matter, invisible but present, holding the universe together. There is dark energy pushing space apart. And there are quantum fields filling every point in space, vibrating with virtual particles, fluctuating with vacuum energy. Space is not a stage. It is an actor participating in the events it contains. This means that the vacuum has properties. It has energy. It has pressure. It can change. And if the vacuum can change, then the laws of physics can change because the laws depend on the properties of the vacuum. In a different vacuum state, electrons might have different masses. Photons might travel at different speeds. Gravity might be stronger or weaker. The universe we observe is the result of one particular vacuum state, but other states are possible, and in some regions of space, in some eras of time, the vacuum may have been different. There is evidence that the vacuum has changed in the past. The fine structure constant, a number that determines the strength of the electromagnetic force, appears to have been slightly different in the early universe. Measurements of light from distant quasars show tiny variations in the constant, deviations that are small but statistically significant. If the fine structure constant has changed, then the vacuum has changed, and the universe has evolved not only in its structure, but in its fundamental properties. This is unsettling because it means that the laws of physics are not eternal. They are contingent, dependent on the state of the vacuum, and the vacuum is dynamic. The universe could undergo another transition, another change of state, and when that happens, the laws of physics will change and everything we know will cease to exist. The transition could happen tomorrow, or in 1 trillion years, or never. We do not know. We cannot predict it. We can only observe and wait and hope that the vacuum remains stable. We have looked at the sky and found that it is dark. This is called Olber's paradox. If the universe is infinite and filled with stars, then every line of sight should eventually hit a star, and the sky should be as bright as the surface of the sun in every direction at all times. But the sky is dark. The paradox is resolved by the fact that the universe is not infinite in time. It had a beginning, and light from distant stars has not had time to reach us. The sky is dark because the universe is young, and because it is expanding, stretching the light from distant stars into longer wavelengths, redshifting it into invisibility. But there is another aspect to the darkness. Even if we account for the finite age and the expansion, the sky is darker than it should be. There is less light, less radiation, less energy than our models predict. Some of the missing light is absorbed by dust, scattered by gas, redshifted beyond detection. But not all of it. There's a gap, a deficit, and the deficit suggests that something is absorbing or blocking the light, something we had not accounted for. One possibility is that the intergalactic medium, the gas between galaxies, is more opaque than we think. Another possibility is that there are more black holes than we have detected, and they are absorbing light before it reaches us. A third possibility is that the universe is not as filled with stars as we assume, that large regions of space are darker, emptier, more void-like than our models predict. And a fourth possibility is that the light is there, but it is not reaching us because space itself is curved or distorted in ways that deflect light away from our line of sight. Each of these possibilities has implications. If the intergalactic medium is more opaque, then our measurements of distances are wrong, and the universe is smaller or younger than we think. If there are more black holes, then dark matter may not be a new particle, but ordinary matter in the form of black holes, hidden from view. If the universe is darker, then the early universe was less efficient at forming stars, and The history of galaxy formation is different from what we have assumed. And if space is curved, then the geometry of the universe is more complex, and the patterns we observe are distorted, warped by the structure of space itself. We have sent signals into space, and we're listening for signals in return. The search for extraterrestrial intelligence has been ongoing for decades, scanning the sky for radio waves, looking for patterns that could indicate technology, communication, a message from another civilization. We have found nothing. The silence is profound. Either we are alone, or we are not looking in the right place, or the signals are there, but we do not recognize them, or civilizations do not last long enough to send signals, or they have no interest in communicating, or they exist in forms we cannot imagine. The silence is also called the Fermi paradox. If the universe is so old and so large and filled with billions of galaxies, each with billions of stars, each with planets, then where is everyone? The absence of evidence is not evidence of absence, but it is suggestive. It suggests that intelligence is rare, or that it is short-lived, or that it is constrained by the same limits we face, unable to travel between stars, unable to send signals across galactic distances, unable to overcome the tyranny of space and time. But there is another explanation, one that is darker. Perhaps we are not alone. Perhaps there are civilizations out there, older than ours, more advanced, more powerful. And perhaps they are silent for a reason. Perhaps the universe is not safe. Perhaps there are dangers, phenomena, forces that eliminate civilizations before they can spread, before they can communicate. Perhaps the silence is a warning, a lesson that we have not yet learned, a reminder that survival requires caution, invisibility, stillness. Or perhaps the silence is not silence. Perhaps the signals are there, but we are not listening in the right way. We're looking for radio waves, for narrowband signals, for patterns that resemble our own technology. But an advanced civilization might not use radio. It might use neutrinos, or gravitational waves, or something we have not discovered yet. It might encode information in the structure of space itself, in the fluctuations of the vacuum, in the patterns of cosmic rays. And we would not recognize it, because we're looking for the familiar, the expected, the echo of ourselves. The universe is vast, and we have explored almost none of it. We have sent probes to the edge of the solar system, a distance of about 20 billion kilometers. The nearest star is 40 trillion kilometers away. The nearest galaxy is 25 quintillion kilometers away. The edge of the observable universe is 100 sextillion kilometers away, and beyond that edge, space continues, possibly forever. We are confined to a tiny region, a speck, and from that speck, we try to understand everything. But we have tools. We have telescopes, instruments that collect light from distant objects and bring it to our eyes, our cameras, our sensors. We have mathematics, a language that describes the behavior of matter and energy, the curvature of space, the flow of time. We have computers, machines that can simulate the universe, calculate trajectories, model galaxies, predict the future. And we have minds, brains that can hold concepts, recognize patterns, ask questions, imagine possibilities. With these tools, we have learned that the universe is expanding, that it began in a hot, dense state, that it is filled with dark matter and dark energy, that it is structured into galaxies and clusters and voids. We have learned that stars are born from clouds of gas, that they burn for billions of years, that they die in explosions or fade into darkness. We have learned that planets form from the debris of stars, that some planets have water, that some have atmospheres, that some might have life. We have learned that time is relative, that space is curved, that matter and energy are interchangeable. But we have also learned that we do not know. We do not know what dark matter is. We do not know what dark energy is. We do not know what caused the Big Bang. We do not know if the universe is infinite. We do not know if there are other universes. We do not know if the laws of physics are the same everywhere. We do not know if time had a beginning. We do not know if consciousness is unique to Earth. We do not know if we are alone. And there are things we suspect, hints in the data, anomalies that do not fit, patterns that should not exist. The cosmic microwave background has cold spots, alignments, asymmetries. Galaxies are too large, too early, too organized. Voids are too empty, too spherical, too vast. Flows are too strong, too coordinated, too directed. Signals arrive that we cannot explain. Objects behave in ways that violate our models. And when we look carefully, when we strip away the assumptions and examine the raw data, we see cracks. The cracks are small. They are not definitive. They could be errors, artifacts, coincidences. Science is built on skepticism, on testing, on repeating experiments until the results are certain. But the cracks are persistent. They do not go away with better data. They do not disappear with refined models. They remain subtle but present, and they suggest that something is wrong, that our understanding is incomplete, that the universe is not what we think it is. One interpretation is that the Big Bang was not the beginning. It was a transition, a phase change, a moment when the universe shifted from one state to another. Before the Big Bang, there was something else. A previous universe, collapsing and rebounding. A colliding brain in higher dimensional space. An eternal inflating background. A quantum fluctuation in a pre-existing vacuum. Whatever it was, it left traces, imprints, scars on the fabric of space and time, and those scars are what we are seeing. Another interpretation is that space itself is older than the matter it contains. Space could have existed before the Big Bang, empty or filled with a different kind of energy, and the Big Bang was the moment when that energy converted into matter and radiation. The structures we observe, the filaments and voids, could be the shapes of space, carved by processes that occurred before matter existed, frozen into the geometry, and now visible as patterns in the distribution of galaxies. A third interpretation is that time is not linear. The arrow of time, the direction from past to future, is an emergent property, something that arises from entropy, from the expansion of the universe, from the way we perceive events. But at the fundamental level, time may be symmetrical or branching or looped. The Big Bang may not be a single event. It may be a recurring feature, something that happens over and over in different regions at different times, and the universe we observe is one instance among many, connected to others in ways we cannot measure. These interpretations are speculative. They are not proven. They may be wrong, but they are consistent with the data, and they provide frameworks for understanding the anomalies, the cracks, the things that do not fit. And they share a common theme. The universe is not young. It is not simple. It is not isolated. It is part of something larger, something older, something beyond our ability to observe. We're looking back in time. Every observation is a look at the past. When we see the sun, we see it as it was 8 minutes ago, because light takes 8 minutes to travel from the sun to Earth. When we see the nearest star, we see it as it was 4 years ago. When we see the Andromeda Galaxy, we see it as it was 2.5 million years ago. When we see distant galaxies, we see them as they were billions of years ago, when the universe was young. And when we observe the cosmic microwave background, we see the universe as it was 13.8 billion years ago, just 380,000 years after the Big Bang. But we cannot see further. The cosmic microwave background is a wall, a barrier, the point beyond which the universe was opaque. Before that moment, photons could not travel freely. They were trapped, scattered by electrons, absorbed and re-emitted, unable to escape. The early universe was a fog, and we cannot see through it. But the fog was not eternal. It cleared, and when it cleared, light began to travel, and that light is what we observe today. But there are other ways to see. Neutrinos can penetrate the fog. Gravitational waves can penetrate the fog. If we could detect the cosmic neutrino background, or if we could observe gravitational waves from the early universe, we could see further back, closer to the Big Bang, perhaps even before it. These observations are at the edge of our technology, but they are not impossible. Experiments are being planned. Instruments are being built. And in the coming years, we may finally see what lies beyond the wall. And when we do, we may find that the wall is not the beginning. We may find that there is structure beyond the wall, patterns, signals, evidence of something older. Or we may find nothing, a smooth, uniform background consistent with our models, confirming that the Big Bang was the start of everything, that before it there was nothing. Either result would be profound. Either result would change our understanding. But there's also the possibility that we will find something unexpected, something that does not fit any model, something that defies explanation. This has happened before. The expansion of the universe was unexpected. The acceleration of the expansion was unexpected. Dark matter was unexpected. Dark energy was unexpected. Every major discovery in cosmology has been a surprise, a deviation from what we thought we knew. And if history is any guide, the next discovery will also be a surprise. The universe does not care what we expect. It does not conform to our models. It is what it is, and our task is to observe it, measure it, understand it as best we can with the tools we have, knowing that our understanding is always incomplete, always provisional, always subject to revision. We are pattern recognition machines. Our brains evolved to find patterns, to see faces in clouds, to hear voices in wind, to detect predators in shadows. This ability kept us alive. But it also makes us prone to seeing patterns that are not there, to finding meaning in randomness, to interpreting noise as signal. We must be careful. We must test. We must repeat. We must distinguish between what is real and what is imagined. But we must also be open. Open to the possibility that the patterns we see are real, that the anomalies are not errors, that the universe is stranger than we think. Science requires both skepticism and imagination, doubt and curiosity, caution and courage. We must question everything, but we must also be willing to follow the evidence, even when it leads to uncomfortable places. The evidence is leading us to uncomfortable places. It is leading us to the conclusion that the universe is not self-contained, not isolated, not independent. It is leading us to the possibility that the Big Bang was not the beginning, that time extends further back, that space is larger, older, more complex. It is leading us to the realization that we are embedded in a structure we cannot fully see, influenced by forces we cannot fully measure, part of a history we cannot fully know. And it is leading us to silence. The silence of the data, the silence of the sky, the silence of a universe, which does not answer our questions, does not confirm our theories, does not provide closure. The universe simply is, and it continues, expanding, evolving, changing, indifferent to our presence, our curiosity, our need to understand. We are alone in that silence, looking out at the stars, searching for meaning, for connection, for evidence of something beyond ourselves. And what we find in the data, in the patterns, in the anomalies, is a suggestion that we are not the first, that something came before, that the universe remembers. Space is hiding evidence, not hiding it intentionally, not concealing it with purpose, but hiding it nonetheless in the limits of our instruments, in the noise of the data, in the vastness of distance and the depth of time. The evidence is there, faint, scattered, incomplete, waiting to be found, waiting to be interpreted, waiting to be understood. And perhaps when we finally understand, when we finally see what the universe is trying to show us, we will realize that the question was never whether the universe had a beginning. The question was whether that beginning was ours, or whether we inherited it from something older, something that existed before time, before space, before the laws of physics themselves. The light continues to travel. The galaxies continue to move. The voids continue to expand. And we continue to watch, measuring, calculating, wondering, knowing that the answer, if there's an answer, lies just beyond the edge of what we can see, in the darkness, in the silence, in the space between the stars, where the universe keeps its secrets,